Alright, so this next section is going to be kind of a pain. It's just basically a long division, but that's just one of the ingredients when we actually have to do an entire graph. Yeah, that'll be some work, but one of the steps is long division. Long division isn't super bad, but there's a fair amount of writing that you're going to have to do, and it takes up some space on your paper, and you just have to do it. So I just want to illustrate the big picture, and that is, well, when does something almost look like a diagonal line? Well, here you have a diagonal line plus something that, when x is large, like imagine that you're dividing by 1,000,000. If x is 1,000,000, this is 1,000,002, 1 divided by that. This gets very tiny when x is large positive or large negative. The overall shape is we have 2x plus 1 plus a tiny bit. So here's 2x plus 1, that's this dotted diagonal line. We saw earlier that 1 over x plus 2, that's when x approaches -2. 1 divided by a very tiny number. It can be either positive when you have positive stuff or negative when you have negative stuff. That's this vertical asymptote. But the slant asymptote is because that's the end behavior. When x is very large, here's 2x plus 1. We have 2x plus 1 plus a tiny bit. That says that the function is just, instead of 1 over x being like this, well, 1 over x plus 2x plus 1 would push it not towards a horizontal line, but toward a diagonal line. And this happens when you can write if you were to do long division and write it this way, that's exactly when this happens. And when does that happen? That's when, well, if you express your rational function in standard form, well, the denominator has to be 1 less degree than the numerator. So long division is the process that goes in the other direction. So the degree of the numerator is 1 more than the degree of the denominator. That's an x to the first, or just plain old x plus 2. And, well, okay, so you can go from this one to this one, or vice versa. If I had it in this form, this is just an illustration that if I had it in this form, I wanted to put it in rational function standard form, I would just find this common denominator of x plus 2 by multiplying the 2x plus 1 by x plus 2 over x plus 2. And common denominators is how you get it into standard form. And then vice versa, or kind of going the other way around, if I have a rational function in standard form, but I want to rewrite it this way, in like sort of oblique asymptote form plus remainder. If I want to write it in this form, and long division does exactly that. I divide, I get a whole part that's like a polynomial. So because the degree is exactly 1 more, I get a first power of x for the quotient. And then the remainder is some remainder divided by the denominator. Okay, so I just want to jump into an example here. I started with it in this form because that one's easier to understand, but usually they're going to be given to you in that just the big fraction combined. And then, yeah, it has to be long division. Maybe it's been a while, but we can do it. It is very similar to what you do with just plain old numbers, but your organization and your setup for that has to be a little bit different. If you know about synthetic division, well, there are a couple of things to be wary of, so I'm not going to go there. Synthetic division only works when the denominator is in a very specific form, and you have to get it exactly right, or else you can't even do it that way. You have to set it up just right. And I just want to do long division because long division is always just plain old long division. Synthetic division is faster when it works, but when the format is wrong, it's problematic. So here is okay, the numerator, and one thing about long division is you want to make sure you absolutely have every single power of x accounted for, which might include writing down a 0 term for like the last one, or anything in between. So if x were missing, I would want to have a placeholder just so things line up well. It's very awkward to get things to cancel and line up properly, and it's very easy to make mistakes if you don't have your columns. There's like a very particular structure that we want to take advantage of by having it all set up that way. All right, so we want to see dividing means what do I have to multiply the denominator by to get the numerator? So how many of these do I need to get x cubed? Well, I could start with the x's because I know I need x. X times the divisor. So x times this, I'm subtracting an x cubed. X times 5x is, I'm subtracting negative 5x squared. And then I'm subtracting a negative 14x. So there's this big minus on the outside, so I get a 0 here, but then it's plus. This becomes plus, this becomes plus. That minus on the outside says that this one becomes minus. So that minus on the outside, I sort of take that into account exactly once for each term. So now I've got, instead of minus 5x squared, I've got plus 5x squared. And then so I'll have negative x left over. And anything that has not been gotten rid of yet, I have to carry that down as well. And what do I need? I need a plus 7. Then I still need 7 of these to get rid of the 7x squared. And what do we have? We'll have minus 7 of these, negative 35x, then, oh, that's a big number, so 70 plus, so that's 98. So subtract, double negative means we get plus 34x, then double negative again, I get plus 38. Okay, so f of x is 1x plus 7, and then remainder divided by the denominator. So the remainder, the whole goal is that the remainder is always of lower degree than the denominator, because if there were highest degree stuff left over, it would have ended up accounted for over here. So now we've got like a proper fraction. The denominator is bigger, so this is negligible when x is large. When x is large, this is tiny, and then you get basically x plus 7. So So if absolute value of x is large, because x is a large positive number or a large negative number, then the f of x is approximately x plus 7, and then you get this other thing. Sure, for small x's, this 34x and then 98, that could be a big number, but eventually the denominator is really big, and the x plus 7 is the main feature that kind of determines everything. Yeah, that's sort of it. I think that's kind of it. I think we'll see this again when I do a couple of graphing examples, and those will be kind of lengthy. But that's kind of for the topic itself. There's really not anything more to it. If maybe the only thing I want to say is just don't confuse it with the other ones here. This one has a horizontal asymptote. Y is equal to 2/3. It's 2x to the 4th over x to the 5th minus 7x to the 4th plus 7. So remember what happens here. The denominator is winning by a lot. The denominator and the numerator are equal degree, so the coefficients balance out. You get 2/3. This one, the denominator has larger degree, so you get y equals 0. The brand new thing that we just saw is the numerator is exactly one more than the denominator. Well, if the numerator has larger degree, you can do long division, and you'll get a polynomial for the quotient. But the linear case is kind of interesting because that's a nice thing that you can graph very easily, and you can just look at it and see that x plus 7 is a line, and that's pretty cool. And but for if the numerator, if this were x to the 4th, sure, we could do long division and we'd get a parabola for the main primary part and then the remainder. But our book doesn't go that far. Or our book, there was like one or two, but for the test, it's kind of we draw the line here. That's kind of good enough. So. Yeah, so that's sort of it.